Welcome back, guys. In this video we are discussing implicit differentiation. If you're nervous because implicit differentiation was challenging in Calculus 1, don't be. It actually turns out that since we know how to take partial derivatives now, and because we have the chain rule, implicit differentiation is much easier than it was in Calculus 1. So we're going to review the Calculus 1 process of implicit differentiation and then see how that generalizes to some function, to a relation given in this way. So we might have some function of x and y equals 0, and we might know that this defines y as a function of x on some small interval. Well, we can find the derivative of y with respect to x using the partials of this function capital F, and I'll show you how that works in a little bit. Or if you have a function of x, y, and z, and maybe this relation implies a relationship between z and x and y. So maybe z, we're considering z as a function of x and y. We can use the chain rule to find the partials of z with respect to x and z with respect to y, just given this relation. So that's where we're going. Let's look at the Calc 1 process of implicit differentiation. Whenever I teach this material in Calc 1, I always start with this example. It's the easiest example. Everybody can wrap their minds around it. If I have a circle of radius 2 centered at the origin, well, it looks like this, right? We go plus and minus 2 units in the x direction and plus and minus 2 units in the y direction from the origin. Now, if I want the slope at any point on this circle, I can use implicit differentiation to find it. Now, if I'm looking for the slope, let's say over here, well, over on a small interval around that point, y is a function of x. Or maybe I'm interested in the slope over here. Well, on a small interval around that x value, y is a function of x. At any part of this curve except for over here, where we've got vertical tangent lines, y can be defined as a function of x. So we might say that this implies a relationship between x and y. It's a relation between x and y. But if I assume that y depends on x, I can find the derivative of y with respect to x by differentiating both sides, differentiating implicitly. So we'll assume that y is some function of x, and then we'll substitute into our formula. So we've got x squared plus y squared equals 4, and we're replacing y with this function of x. Now, most of the time when we're doing implicit differentiation, we don't do that. It's sort of implied that we do that, but I just wanted to make it explicit for this video. And then we take the derivative of both sides with respect to x. So we're differentiating both sides with respect to x, remembering that y is a function of x. Now, it's very easy for Calculus 3 students to forget that y is a function of x because we've been taking all these partial derivatives, but this is an ordinary derivative. So if y depends on x, I have to use the chain rule to take the derivative of this piece. When I'm taking the derivative of this side, derivative of x squared is 2x. The derivative of this function squared is 2 times the function times the derivative of the inside with respect to x, and that equals the derivative of 4, which is 0. Most of the time we would just say the derivative of y squared with respect to x is derivative of y squared with respect to y, which is 2y, times dy over dx, the derivative of this variable with respect to this variable. But again, that comes from the chain rule. It's because we're remembering that y depends on x. Or we're saying, well, if y depends on x, what is the slope? How do I get this? Well, now I'm trying to get when I'm using implicit differentiation, remember our goal is to find this dy dx. So I want to get this guy by itself. That's easy enough. It's just a linear equation, very simple. To get this by itself, I need to subtract the 2x from both sides. And then divide both sides by 2y. That's how we did it in Calc 1. So we differentiated both sides with respect to x, remembering that y is a function of x, and then we did some algebra. We just solved for dy dx. And this gave us the slope on our curve. It gave us the slope over here. So let's say that x and y are both square root of 2. So I've got square root of 2 squared, which is 2, plus square root of 2 squared, which is 2. 2 plus 2 is 4. Excuse me. So I'm talking about the slope of the tangent line right there at root 2, root 2. Well, according to this formula, the slope at that location is negative x over y. So we get a slope of negative 1. And it looks like the slope is probably negative 1 there, right? Rise over run or fall over run. Looks like we go the same number of units in the x direction as we go down in the y direction. So the slope is negative 1. So that's how we did it back in Calc 1. Now I want to talk about the same idea, but given the fact that we understand partial derivatives now. So I've got this relation, f of x, y equals 0. Like in this example, the f of x, y is x squared plus y squared minus 4. So I would just set one side equal to 0 because we're used to that. And the function of two variables is on the other side. We just have a convention whenever we're talking about implicit differentiation to make this a capital F. It doesn't signify anything special. It's just a function of two variables. Now we're going to differentiate both sides with respect to x. And remember that y depends on x, so maybe I should, let's put d dx over here as well. Maybe I should make that a little bit more explicit. Just to remind myself that y is a function of x, I'm going to replace that y with y of x. Well, according to the chain rule, when I have a function of two variables like this, the derivative of that function of two variables with respect to x is the derivative of that function with respect to the first variable, or excuse me, the partial of that function with respect to the first variable, times the derivative of that variable with respect to this variable, plus the partial of this function with respect to the second variable, so that's y, plus the derivative of that variable with respect to that variable. And the derivative of 0 is 0, of course. Now the derivative of x with respect to x is of course 1. So we end up with the partial of f with respect to x plus the partial of f with respect to y times dy dx equals 0. And that's exactly what we had over here when we were doing this in Calculus 1. If I'm taking the derivative of something with respect to x, well, I take the partial with respect to x times this, which is 1, plus the partial of this with respect to y times the derivative of the inside, which is this. And now we're here. And if I want to get dy dx by itself, then I just subtract this from both sides and divide by that. Now, of course, this only works if these partials, if the partial of f with respect to y is not 0. There are some other requirements. Some requirements on f, this capital F, that I'll list in just a second. So, under certain conditions, this is true. That always bothered me when my professors said that in school. They're like, this is sometimes true. Most of the time it's true, but sometimes it's true. And they're like, when is it true? I want to know when it's true. There's a theorem in advanced calculus called the implicit function theorem. It just gives you the conditions when this is true. Basically saying, okay, when can we assume that y is the function of x and then take its derivative? Well, a couple of things have to be true. This works when f of xy is defined on a disk so that's just some open circle containing a point of interest. So maybe we're interested in this derivative near x naught y naught. So this function has to be well defined on some little disk that contains x naught y naught. So here's x naught y naught. I'm going to put a little disk around it. It's in the xy plane. Every xy is associated with a z that's given by capital F of xy. So this function has to be well defined there. And we're listing the conditions of the theorem. What else has to be true? Well, f of x naught y naught must be 0 so that this first part is satisfied. And of course the partial of f with respect to y, that's this expression in the denominator, at x naught y naught can't be 0. And fourth condition, the partials of f with respect to x and y must be continuous on the disk. So provided all of that's true, y can be thought of as a function of x near x naught y naught. So we're on any part of this little curve. Over here, the function x squared plus y squared plus minus 4 equals 0. That's our f of xy. Its partials with respect to x and y are 2x and 2y. Those are continuous near those points over here. Y is not 0, so we don't have to worry about that. If I evaluate f of xy at any point on this curve, I'm going to get 0 because of the way we defined f of xy. And of course we're not dividing by 0. That means this little part of the curve defines y as a function of x, and that's its derivative. So as long as all of this is true, this holds, and this holds most of the time. Okay, so if you were curious, those are the conditions. All right. Now let's apply this. We applied it to this simple problem over here, and I hope you can see that it's exactly the same thing that we were doing here. We said, well, what's the derivative of f of xy with respect to x? Well, I took the derivative term by term with respect to x. The derivative with respect to x, and then I added the derivative with respect to y, that's the derivative of the outside, and then I evaluated it, or I multiplied it by the derivative of the inside by the chain rule. And that gave me this. Or we can also think of it as applying the chain rule just to this function of two variables right here, and that d dx, that derivative of x with respect to x, of course, is 1. And then you solve for dy dx. So there's our derivative of f with respect to x, it's 2x. And there's our derivative with respect to y, it's 2y. So that's just a special case of this. Let me show you another example. So let's say we've got y times cosine of x equals x cubed plus y squared. And we want to find dy dx. We could use implicit differentiation from Calculus 1, or we can use the method that we just talked about. So let's use the method that we just discussed. Let's move all the terms to one side, and that will be f of xy. So f of xy is y cosine of x minus x cubed minus y squared. And that's been set equal to 0. Now I just need to take the two partials. Let's write down what we're doing. Set one side equal to 0. And then the left-hand side should be defined to be f of xy. And now we're going to compute those partials. Compute the partial of f with respect to x and the partial of f with respect to y. This is our problem statement. Now I'm computing the partials. Now y is a constant, so I bring that down. The derivative of cosine of x with respect to x is negative sine of x. This is because I'm taking the partial of f with respect to x. This is not a derivative. Y is not implied to be a function of x in this context. I just take the partial with respect to x. And then the derivative of negative x cubed with respect to x is just 3x squared. There are no x's here, so the partial of y squared with respect to x is 0. Then I take the partial of f with respect to y. Now this is just a constant times y. The derivative of a constant times y is just the constant. There are no y's here, so the derivative of x cubed is 0. And the derivative of negative y squared with respect to y is just 2y. So after you compute those two partials, you just substitute into the formula. Derivative of y with respect to x is the negative partial of f with respect to x over the partial of f with respect to y. Now notice, this dependent variable is y, and I've got the partial of f with respect to that dependent variable in the denominator. So that variable is down here. And the independent variable in this case is x. Its derivative is up here. And we have got the negative sign out front. And again, that negative sign comes from applying the chain rule to this function. Take the derivative of this with respect to x times 1 plus the derivative with respect to y times dy dx by the chain rule, and that has to be 0. Okay, and then you just rearrange it to get dy dx by itself. All right, so now let's substitute in all the pieces. I need to substitute in the partial of f with respect to x, and the partial of f with respect to y. Distribute the negative. And that's our formula for the slope. So now if I want the slope at any xy that satisfies the original equation, I can just substitute it into this formula down here. Provided the denominator is not 0, we're good to go, and that's going to give us the slope there. So we just computed those two partials, and then we substitute into the formula. It's very simple. Okay. Now similarly, if we have a function of x, y, and z, set equal to 0, or if there's terms on this side, we can move them over. We can think of z as a function of x and y under some conditions. And they're pretty much the same conditions as before, those that we stated for the implicit function theorem before still hold here. But now I've got a function of x, y, and z. So we need the function of x, y, and z to be well defined. It's not going to be on a disk anymore, it's going to be on an open ball, basically. It's like the 3D analog of this disk. It's the interior of some sphere centered at x naught, y naught, z naught. We need the function evaluated at x naught, y naught, z naught to be 0 so that it satisfies this equation. And the partial of f with respect to z at x naught, y naught, z naught can't be 0. And then all the partials of this function with respect to every variable that's listed here. There are two variables here, so we've got partial of f with respect to x and y. Those both have to be continuous on the disk for this implicit function, for this derivative to work. The partials of f with respect to x, y, and z would have to be continuous on the open ball for the other one to work. So those are the under some conditions, and if you're really curious about it, come see me during office hours and we can talk about the implicit function theorem. If z is a function of x and y, I might be interested in finding its partials with respect to x and y. So let's take a composition of functions here. If I want to know the derivative of this function with respect to x, I can use the chain rule to find it by differentiating both sides with respect to x. And of course the derivative of 0 with respect to x is just 0. Now the derivative of this side with respect to x is the partial of f with respect to x times the derivative of x with respect to x plus the partial of f with respect to y times the derivative of y with respect to x plus the partial of f with respect to z times the partial of z with respect to x. That has to be 0. Now, we're assuming that x and y are completely independent variables. So this guy is gone. That guy is not going to appear at all in our formula. Because y doesn't depend on x. Y does its own thing. So all we would see is this. And of course this is 1. So we've got the partial of f with respect to x, I'm going to use subscript notation now, plus the partial of f with respect to z times the partial of z with respect to x equals 0. So it's kind of like we did in Calculus 1. You looked at this and you said, okay, I'm going to go across this function. Every time I see a function or I see a term that involves just an x, I differentiate with respect to x. I get that answer. And then if I see a term that involves z and z depends on x, I take the derivative of the outside with respect to z. So I take the partial of this function with respect to z. And then I multiply by the derivative of the inside with respect to x, treating y as a constant. Since we're treating y as a constant, this guy is 0, and we've got a partial right there. So if I solve this for the partial of z with respect to x, I get this. Notice that I've got the partial of f with respect to z in the denominator, and the partial of f with respect to x in the numerator, and then the opposite sign. That opposite sign comes from the fact that I have to move that over. I'm subtracting it from both sides, and then I'm dividing by that. Now, similarly, we could look at f of x, y, and z of x, y, and take the derivative of both sides with respect to y. Now we're assuming that x and y are independent variables, So this term, it doesn't need to be there. I'm taking the derivative with respect to y. Anything that just involves x is going to be 0. It's gone. Then I'll take the derivative of everything here that I see here with respect to y. And then every time I see something involving z, I'll take the derivative of the outside with respect to z, and then multiply by the derivative of the inside with respect to y. But z depends on two variables, so this will be the partial of z with respect to y, treating x as a constant. And that equals 0. So when I get partial of z with respect to y by itself, I end up subtracting that from both sides, and then dividing by that, and we get this formula. Again, notice the dependent variable is z. The partial of f with respect to the dependent variable goes in the denominator. And my independent variables here are x and y. The partial of f with respect to the independent variable goes in the numerator. And we always have that negative sign that comes from moving this term over to the other side. Okay, so these are our formulas under the conditions that we talked about. And those are the conditions given by the implicit function theorem. If you feel like nerding out and you want to go to Wikipedia and study up on this stuff, more power to you. There's some interesting stuff out there about implicit function theorem, I'm sure. If you're more interested in that, you can take advanced calculus. In advanced calculus, you will learn more about the details of that theorem and why it's true. Okay, so now I've got these two formulas, and I can apply them to find partials of z with respect to x and y anytime I have a relation like this. It's pretty nice. And again, it's just like we did in Calculus 1. It just requires a little bit less thinking. All you're doing is computing some partials and then substituting them into a formula now. But it's completely equivalent to what we did in Calculus 1. Now we just have a few more variables. A variable or two more than you're used to. Okay, so let's say we've got e to the z equals x times y times z. And you're asked to find the partials of z with respect to x and y. Well, in order to do that, we need to find capital F of x, y, z, and find its partials with respect to x, y, and z, and then just substitute into those two formulas. It's actually very simple. So first you find f of x, y, z by moving all of the terms to one side. So you've got e to the z minus x times y times z, and we'll say that that equals 0. So that's our first step. And then we're going to compute those three partials. Compute the partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z. The derivative of e to the z with respect to x, treating y and z as constants, is 0. And then the derivative over here, that's just the derivative of a constant times x. The derivative of a constant times x is just our constant. The constant is negative yz. Now over here, there are no y's in this, so its derivative is 0. This is the derivative of a constant times y. The derivative of a constant times y is just the constant. And now I'm taking the derivative of the same expression with respect to z, treating x and y as constants. there is a z in this, so the derivative of e to the z is e to the z. And then for this term, I've got a constant times e to the z. The derivative of a constant times e to the z is just the constant. All right, so we've computed those three partials, and we're going to substitute them into these formulas, and then we'll be done. And just to even save some paper, I think I'm going to write my answer up here. So partial of z with respect to x is the negative partial of f with respect to x over the partial of f with respect to z. So this is a -1 times negative yz, all divided by e to the z minus xy. So that is our partial of z with respect to x. That's how z changes. That's the instantaneous rate of change of z as x goes up by 1 unit and y is held constant. So if you give me an x, a y, and a z that are on my surface, a surface that satisfies this equation, then this is how much z increases as x increases by 1 unit at that particular location, at that point on the surface. The partial of z with respect to y is similar. Since I'm taking derivative with respect to y, I get the partial of f with respect to y in the numerator. The dependent variable is z, so we've got the partial of f with respect to z in the denominator. You just substitute. Partial of f with respect to y was negative xz. Partial of f with respect to z is this guy down here. So I have e to the z minus xy. The two negatives multiply to give us a positive. And that's the partial of z with respect to y. Okay, and that's implicit differentiation. You just find the capital F, you compute all of its partials, and then you substitute into the appropriate formula to get your final answers. Now, we did not do any examples of finding the slope of the surface in the x or y directions, but if I had a particular x, y, z that satisfied this equation, we could find the values of the partials at that point. So let's just do that one example just to finish this. Let's say somebody asked you to find the partial of z with respect to x at x equals 1 y equals e, z equals 1. And let's just check and make sure that's on the surface. We had e to the z equals x times y times z. At 1e, 1, replace z with 1, replace x with 1 and y with e. Get e equals e, that checks out, so that's a point on the surface. Now if I want a slope in the x direction at that location, I just go to this formula here and I plug in that point. So I'll evaluate the partial of z with respect to x at that location. So y is replaced by e, z is replaced by 1. So I've got e to the z, which is 1, minus x times y. Ooh, whoops. At that location, we're dividing by 0, so actually we can't find the slope there because that partial of f with respect to z is 0 at that location. So can't do that. Let's see. Let's try to figure out one that won't give us a 0. Well, actually, it's going to be a little bit too involved. But if you could find an x, y, z that satisfies this, so that the partial of f with respect to z is not 0, we could find the partial of z with respect to x at that location by just substituting into this formula. It doesn't work at this point, though, because then I have e minus e in the denominator, and that's not allowed.